negative feedback circuit is a circuit much like a positive feedback circuit, except that the conduction path is between the inverting input terminal and the output terminal. So we're going to work an example. So let's say that I have the following circuit. Notice that I've put the inverting input terminal on top. That doesn't change the operation of the amplifier in any way, shape, or form. It's just making it slightly easier to draw. Our op amp is still going to need power. Exactly right. So for positive feedback, the feedback resistor. So let's call this guy up here. Oops, don't know what the hell just happened there. R sub F for now for feedback resistor. And it's a negative feedback resistor because it's connecting the inverting terminal to the output terminal. For positive feedback, which is what we covered on Wednesday, we were connecting the non-inverting terminal to the output. This is going to be our output voltage. The out, I'm going to have some resistor here, which for lack of a better term, I'm going to call R1. And I'm going to apply some input voltage here, Vn. And let's just erase these for now. Let's say that R1 has a value of 5 kiloohms. R2 has a value of 10 kiloohms. The input resistance of our op amp, Rin, is 1 mega ohm. The output resistance of our op amp is 100 ohms. Our open loop gain, AVOL, is 10 to the 5th volts per volt. And our input voltage here is simply a value of 1 volt. We're going to analyze the circuit. We're going to determine multiple different quantities. Okay, so we're going to get a little bit more in depth than what we did back in circuits 1. We're going to start with determining our output voltage V out. Then I want to know what our closed loop gain is. So this closed loop gain is simply V out divided by Vn. I want to know what the resistance Rin is. So I'm using little or lowercase r here. So what this resistance Rin is the resistance that's seen by our input signal. Okay, so what we see looking in, which is going to be different than the input resistance of the op amp by itself because we have this feedback network applied. Similarly, I want us to find R out, which is the resistance seen looking into the output terminal of our system. And lastly, I want us to figure out what our differential voltage VB is for the set. So at least 3 of these things are new-ish to you, all right? So the output voltage, that's fairly straightforward. We've been dealing with output voltage all the time. We've been doing a lot with differential voltages as well, so that one's fairly straightforward. But these three guys in the middle, the closed loop gain, the input resistance, and the output resistance are all probably new. And the reason that we weren't able to define any of these quantities for any of our previous circuits is because this is the first one where we actually expect our op-amp to behave as a linear device. In every other situation that we've used it, it's been operating in the non-linear region. And we're going to use Thevenin's theorem to figure out what this input resistance and output resistance is. And Thevenin's theorem requires us to have a linear two-terminal network. So these quantities don't make any sense for positive feedback amplifiers or open loop amplifiers because they are inherently non-linear for the overwhelming majority of their operational range. This closed loop gain also depends on linearity because we need it to not be operating in a saturation region where some change in the input voltage actually causes a change in the output voltage, which is not something that we've experienced with the previous circuits, okay? So these are three new parameters that we're only really gonna ever have to deal with for a negative feedback op-amp circuit, because negative feedback op-amp circuits are intended to work as an amplifier, linear amplification. You put 1 volt in, you get a scaled version of that 1 volt output. All right, so we're going to start by using the practical op-amp model. All right. So I'm going to redraw our circuit using the practical op-amp model. And as always, I will start with the practical model itself and then add things to it. So here is our input resistance Rin. This is the input resistance of the op-amp itself. This terminal represents, actually, I'm going to take that back. This top terminal is going to represent the inverting input terminal. This bottom terminal is going to represent the non-inverting input terminal, which means our differential voltage VD will now have positive polarity on the bottom, negative polarity on the top, because VD is always the potential difference between the non-inverting terminal and the inverting terminal. I'm drawing Rin upside down to make it easier to draw the feedback that's going to happen. Does not matter if we draw it the other way around or anything. It's just going to make the overall drawing look a little less messy by doing it this way. So just explaining what I'm trying to do here. Over here, I'm going to have AVOL times VD. Then I have output resistance of my op-amp, the output voltage of my op-amp, and here is my reference. So that's my practical op-amp model with a small change. Let me scroll up here real quick. So our output voltage in this particular case is an open circuit output voltage. We don't have any load resistance or anything, so we can leave this guy alone. We can see that our non-inverting input terminal is connected directly to ground. So I'm going to connect my non-inverting input terminal directly to ground. Between my inverting input terminal and ground, I have a resistor R1 in series with my input voltage source. So here's my resistor R1. Here is my input voltage source. And between the inverting input terminal and the output terminal, I have that feedback resistor RF. like so. So let's start. Does this representation make sense? Anything not confusing or anything like that? So redrawing makes sense. All right. So we have a couple of different unknown voltages here. So we are going to wind up applying Kirchhoff's current law at two nodes very specifically in order to solve this. Okay. We're going to apply Kirchhoff's current law at the inverting input node. And we're going to apply Kirchhoff's voltage law at the output, or excuse me, current law in both cases at the output node. So we're going to add this current together, if it will write, there we go. This current and this current. We're going to write an equation for this current and this current added together, get a system, solve said system, and we should be able to figure out all of our unknown voltages. So applying KCL at our inverting input, and I'm going to substitute the values for things in here. So we're going to have the voltage at our inverting input, which we don't know, V minus our input voltage of 1 volt, divided by our RN value, or excuse me, R1 value of 5 kilo ohms, plus V minus the nodal voltage at our inverting input terminal, minus V out, divided by our feedback resistor RF, which in this case is 10 kilo ohms, plus V minus V plus, where we know that the voltage present at our non-inverting input terminal is ground, so it's just V minus 0, divided by the input resistance of our op amp, which was 1 mega ohm, thank you, is equal to 0. So that's our first equation. We can apply KCL at our output, and we'll find that we have a current to the left, which is V out minus AVOL 10 to the 5 multiplied by VD. So what's VD in this case? Justin, you have any thoughts? It's a negative V minus, right? Because it's 0 minus V minus. Yeah. So negative V minus divided by our output resistance of 100 ohms. And then we're going to have the current flowing through our feedback resistor from right to left, which should be V out minus V minus divided by 10 kilo ohms is equal to 0. There's our second equation, and we should now be able to solve and determine V minus and V out. So if we solve this guy, I got a voltage of 20.199 microvolts for V minus and a voltage of negative 1.9999392 volts for V out. You guys can take a moment to verify that on your calculators if you choose to do so, or we can move along.
I saw a video that said V out, you can do the gain and then you can just do V out is gain times V out.
Very, very true. Okay, so let's talk about that for a moment. When we deal with an ideal op amp, which we are not yet doing, we will find that the output voltage is nothing more than the closed loop gain times the input voltage. But we don't yet know what the closed loop gain is. We only know the open loop gain. So if we were dealing with just the open loop gain, we'd be facing that same conundrum that we talked about at the very beginning of this class, okay? We have an input voltage of 1 volt. We have an open loop gain of 10 to the 5 or 100,000, which means that we would expect the output voltage to be 100,000, but we know that can't be true. Okay. So what negative feedback is doing is bringing that open loop gain of 100,000 down to a manageable level so that we have linear amplification occurring. Okay. So we can obviously see the answer to one of our questions already. We've determined V out to be negative, not quite 2 volts, but very, very close. We can figure out what our closed loop gain is right now.
I couldn't have just done the negative of the feedback resistor over the input resistor.
Not without understanding why we can do that using the ideal op amp rules.
So we can't do that because this is not an ideal.
Exactly right. So this is a practical op amp. But we're going to see, kind of jumping ahead a little bit, that practical op amps, even kind of poorly designed practical op amps, will be very, very close to ideal op amp behavior. All right. So the answer to part A, what our output voltage is this guy right here. Part B, I believe, was asking us what our closed loop gain was. Well, I chose an input voltage of 1 volt for a very specific reason. So for part B, our closed loop gain, AVCL, is simply V out divided by VN, which is negative 1.9999392 volts divided by 1 volt is negative 1.9999392 volts per volt. And because of Cheston's, I'm going to call it an observation, this is very close to that resistor ratio RF over R1 for this particular amplifier circuit. Brandon.
Are we not just rounding too because we want to account for R out? That R out makes it drop very, very slightly to 1.9999.
I'm not rounding it to 2 because I want to show you that there is a small difference between the practical behavior and the ideal behavior. Right, so this 20.199 microvolts, that's really close to 0, which is what we would expect for an ideal op amp, but it's not technically 0. So that's why this isn't technically just 2. I think we can jump ahead to the answer for part E as well. Our differential voltage, VD, is just negative V minus. So in this case, that's negative 20.199 microvolts. And so now we have those two Thevenin resistances that we need to look at. All right. So I want to scroll up here real quick. The first of those resistances that we're looking for is the input resistance seen by the source, okay? So using Ohm's law, we can say pretty easily that, let's call this current right here IN. Our resistance lowercase rn is just going to be Vn divided by I. All right. So we're just looking for the Thevenin equivalent when we already know what the open circuit, or excuse me, what the voltage is there. Okay. All right. So how do we determine what IN is? The voltage drop over R1 divided by the resistance of R1, right? So it's simply going to be Vn minus V minus divided by R1. This went too far. So Vn minus V minus divided by R1, and then we have a Vn up here. And so that's going to look like 1 volt divided by 1 volt minus 20.199 microvolts all over our resistor value of R1, which is 5 kiloohms, which gives me a value of 5,000.100997 ohms, or really close to just that 5 kilo ohm resistor itself. And for our output resistance, R out, that one's going to be a little bit trickier. Okay. So the output resistance, lowercase r out, is resistance seen looking in. Okay. Now, our practical op-amp model contains a dependent source, which means we can't just look in and figure it out. We have to use the ratio of the Thevenin voltage divided by the Norton current to figure out what we see here. Or we could do a test source method, but I'm not going to do that. The reason why I'm not going to do it is because we already know what the open circuit voltage is. It's just V out, right? So V out and V Thevenin are the exact same quantity, so there's no point in solving for it again. So we need to analyze this circuit. Now, under the constraint, let me do this in a different color. So we're going to reanalyze this guy with our terminal shorted and figure out what this current I Norton is going to be, because that's the other piece of information that we're missing. How does that change our analysis? So let's look at this first equation specifically. What changes?
V out is connected to ground now.
Yeah, exactly right. V out is connected to ground, so V out is 0. So we can use this equation with V out is equal to 0 to solve for our new value of V minus under the constraint that this output is shorted. And then we could simply say that the current flowing through the feedback resistor plus the current flowing this way add together to make I Norton. Does that make sense? So just Kirchhoff's current law application at this node. So we would have, let me find my stuff here. V minus minus 1 volt over 5 kilo ohms plus V minus over 1 mega ohm plus V minus over 10 kilo ohms is equal to 0. We can solve this guy and we'd find that V minus is 0.66445 volts. So short circuiting our output causes a heck of an increase in this voltage. Effectively, that voltage is having to adapt to force that output voltage to go to 0, which is a method that's used to test certain parameters of op amps when they're making their data sheets, all that kind of stuff. Anyway, we could say that I Norton is V minus over 10 kilo ohms plus 10 to the 5 times negative V minus, this is just 10 to the 5 VD, divided by 100 ohms is equal to negative 664.45176 amperes, a ludicrously large current that if that were actually flowing in the op amp would cause it to burn out. And then from this, our output resistance is our V out from our initial analysis divided by I Norton. So in this case, that would be negative 1.999999392 volts divided by negative 664.45176 amps is 3.0085 milliohms. All right, so let's look at what I've defined I Norton to be the current flowing down because my open circuit voltage V out has positive polarity on top, right? So I want the current flowing in, which is V minus minus 0 over RF plus AVOLVD minus 0 over RF.
I thought the arrows would be that low.
No, so these are the arrows from our original analysis. This is for our second bit of analysis to determine lowercase r out. Okay, so some things that we have observed here. For this practical op amp circuit, we see that V minus is very small. Okay. We see that R out, lowercase r out, is very small. And we saw that lowercase r in, where do we have, is approximately equal to the resistance directly connected to our input voltage source. So let's circle back around to that original model that we dealt with way back a week and a half ago and try to figure out what parameters our ideal op amp model should have. So what value of the voltage gain, what value of R out, and what value of RN make our device behave ideally. Okay. So our original model for an amplifier in general was something like this, where we had an input resistance Rn, a dependent voltage source AV multiplied by Vn, and our resistance here are out. So this was our original model. Everything between these red dashed lines, where this voltage we considered to be Vn, and this voltage we considered to be V out. We had a practical voltage source at our input, so let's call this guy Vs. We had some load at our output, RL, and this voltage drop was then VL. And we said ideally, VL should be our voltage gain times Vs. Or our input is simply a scaled version, excuse me, our output is a scaled version of our input. Okay. So the first question that I want to ask you guys is, to make this happen, we really need two things to happen. Okay. We want Vs and Vn to be the same signal. Okay. And then we want AV times Vn to be exactly equal to VL. Under those two constraints, Vs multiplied by AV will give us exactly VL. So how do we make that happen? All right, so let's look at the left-hand side first. What value for Rn will make Vn exactly equal to Vs? Infinity. If Rn is an open circuit, that means no current is flowing in this loop. So there's no voltage drop over our source resistance Rs, and all of Vs is applied at these terminals Vn. So that's one thing. We want R out to be equal to infinity ohms. Sorry, Rn to be equal to infinity ohms, my apologies. Now let's talk about the other side. Okay. What value does this R out need to have so that there's no voltage drop over it? 0. It needs to be a short circuit. So under these constraints, VL is just going to be exactly equal to AV, whatever our voltage gain is, times Vs. Now, this model doesn't tell us anything about what the ideal voltage gain for a closed loop amplifier is, okay, because this is an open loop configuration. And that discussion really exceeds the amount of knowledge that we currently have. So I'm just going to give you the answer. We would want our open loop gain, AVOL, to be infinitely large, or as high as we can possibly get. Because the higher that we make that open loop gain, the more well-behaved it will be as a closed loop gain by the application of feedback. Okay. So let's revisit that last problem using these parameters. So our practical op-amp model is now going to look something like this. So let's start here. So this is an infinitely large resistance. This is still, so let's see if this is B minus. Draw a pen thingy. This is V plus. This is our differential voltage VD. Our non-inverting input was tied to ground, so I'm going to go ahead and draw that. We had our 5 kilo ohm resistor right here. We had our 1 volt source right here. On this side, we have infinity times our differential voltage VD. We have a 0 ohm resistor or short circuit right there. Here's our output voltage, the out. Ground. Here is our feedback resistor. Of 10 kilo ohms. Okay. So before we even start doing our analysis, Brandon, what's up?
The same assumptions that made for the comparator circuit. And our RN to be approaching infinity, our AB approaching infinity, our out to 0 to have a perfect comparator circuit.
To have a perfect comparator circuit, sure, yeah.
To make our piece.
Right, yeah. So we assumed that Rn was extremely large as compared to our biasing resistors when we applied some sort of bias network. Absolutely. So we said that there was going to be maybe some small amount of current flowing into the input terminals, but it really wasn't that big of a deal, right? Our voltage gain, we wanted it to be large so that the linear range was as small as possible. It didn't necessarily need to be infinite or anything like that. But we did want it to be large so that we are getting the most out of our nonlinear operation. And this guy being 0 actually probably didn't matter all that much because there was no feedback or anything like that in the comparator. So there was no place for a voltage drop to really occur anyway with an open circuited output. If we were driving a load though, yes, we would want that value to be small, but it doesn't necessarily have to be 0 levels of small. So yeah, so these ideal op-amp characteristics can be applied a little bit to some of the previous circuits, but what I'm about to do here, so one big problem with just saying, well, I'm going to use the ideal op-amp rules is that one of them cannot be applied or it doesn't make any sense. Okay, and that's what we're about to talk about. So the reason why the output voltage in our positive feedback and open loop circuits was pinned to either VCC plus or VCC minus had everything to do with the fact that our differential voltage was non-zero. And in an ideal op-amp, we will find in just a second that the differential voltage will always be exactly 0. So we can't make that part of the assumption when we're dealing with non-negative feedback circuits, or it messes everything up.
I was just asking because,
Yeah.
for the homework one, I did like a small group.
Yeah, that's fair. Yeah, but we'll find that VD, if VD is 0, the output is 0. And we're going to find that for this circuit, VD will always be 0. So let's prove that real quick. Since we have a short circuit here, V out is exactly equal to infinity times VD. Right? Anybody have any beef with that? So we can observe our output voltage is equal to infinity times VD, which implies that VD is equal to whatever our output voltage happens to be divided by infinity, which will always be 0 volts. So this is our voltage constraint equation. This is where that ideal op-amp rule of there cannot be a potential difference between the input terminals comes from. This is forcing our differential voltage to be 0. So V plus minus V minus is equal to 0, or no potential difference between our input terminals. Right? So with that in mind, and the observation that so we're going to apply Kirchhoff's current law at this node like we did previously. We're going to add this current, and this current together and set them equal to 0. But we should observe that this current right here is the current flowing into an open circuit, which means no current will be able to flow into or out of our input terminals. That's where our other ideal op-amp rule comes from. Right? So if we apply KCL at our inverting input, we get V minus, which will be what in this case? 0, yeah, because we know V plus is ground, so V minus has to be ground because V plus minus V minus is equal to 0. So we're going to have negative 1 volt divided by 5 kiloohms minus V out divided by 10 kiloohms plus 0 is equal to 0, where this plus 0 is from no current can flow into or out of the input terminals. And so if we rearrange this guy, we'll find that V out is equal to negative 10 kiloohms divided by 5 kiloohms times 1 volt, or negative 2 volts. And as Chaston mentioned earlier, the output voltage is simply the closed loop voltage gain multiplied by the input voltage. So what's the difference in this analysis using the ideal model versus the analysis that we did using the practical model? About 0.00006 volts. Yeah. So practically no real difference whatsoever. As it turns out, we have to design a pretty shitty op amp to make the ideal op amp rules not apply in a negative feedback situation, okay? So for homework set number 4, I have you analyze 2 circuits using the practical op amp model. Then I have you reanalyze those circuits using the ideal op amp model and calculate the actual percent error introduced by using the ideal model. And you should see that it's well under 1% in both cases where I'm using very poor op amp parameters. All right, so I think that's going to be enough out of me for today. What we are going to do on Monday will be a quick review of applying the ideal op amp rules directly so that we don't have to redraw the circuit in this hippie difficult way anymore. And then going over those op amp topologies that we talked about in circuits 1, inverting, non-inverting, differentiators, integrators, and all that kind of good stuff again, because as electrical engineering students, now you're going to be tested on being able to identify those specific type of amplifiers and knowing those relationships so that when we get to cascaded op amps, which is our last topic where we're chaining things together, we can break it down into digestible bites of saying, well, I know how this behaves and I know how this behaves. So now I just smash them together and know how everything behaves overall. All righty, I hope you guys have a great rest of your weekend. If you have not yet turned in homework number 1, please do so before midnight tonight. Homework number 2 is due on midnight on Monday, if I'm not mistaken. So yeah, see you guys later.